Welcome everyone. Abhishek will continue to talk about Riemann surfaces. Abhishek, you can start now.
Thank you, Abhay. Okay. Okay, so before going to start, let me mention some updates regarding my lecture notes. So in the first lecture, there are some typos, and I will update it soon. Thanks to Ravi for pointing out these typos. Uh, Regarding the second lecture, so there were two doubts. So, okay. So first doubt was regarding the uniqueness of this conformal structure, so that this projection map is holomorphic. Okay. Basically, I have given the explanation and in the updated lecture notes, so one can go through it. And the second one is regarding this doubt was also asked by Ravi regarding the uniqueness of, so regarding this uniqueness. So Ravi himself pointed out that if we have uh, two maps, let us say G gamma and G gamma dash, you just take this composition. Okay. So for this composition, Y will be a fixed point. Okay. And since this group G is a free group, this has to be identity. So basically, they are the same. Okay? So these two were the doubts. So it will be there in the updated notes. Okay, so today basically the theme is to show that uh, every smooth oriental surface in R3 can be given a Riemann surface structure. Okay. First let me start with some definitions. So by smooth surface in R3, we mean that smooth in R3 is a subset S of R3 such that each point P belongs to S, has a neighborhood diffeomorphic to an open subset R2. Okay. So locally it is diffeomorphic to an open subset of R2. Okay. So basically local diffeomorphism near, let us say, this is okay, a local diffeomorphism near P determines smooth local coordinate. By which I mean a point Q near P has coordinates Q is basically okay. So basically, we are giving a coordinate under this diffeomorphism. The inverse, let us see, capital F of inverse, So this inverse is nothing but it maps some open set of R2 onto some open neighborhood. Okay, of P obviously belonging to S. So this is called a local parameterization. Okay. So basically by let me just clarify this one. So by a diffeomorphism, I mean that a homeomorphism is an F such that F and F inverse are smooth. And by smooth, I mean that all partial derivatives of all order exist. Okay. So let us go back. So now let S be a smooth orientable surface. Okay. In R.
Abhishek,
Yeah.
I have a question. It may be silly. So, for a smooth surface, there can be many local parameterization.
Yeah.
So, is there any canonical kind of choice
Oh
of
yeah,
parameterization?
because basically the transition map will again going to be a diffeomorphism.
Which map?
That's how. Okay, so this is a smooth surface in R3.
Hmm.
The abstract smooth surface is defined as, let me just let it down. So let M be a topological space. Okay, let us say this is Hausdorff and connected. Okay, so we say that, so we have to define a smooth structure on this one. Okay, so for every point P belongs to M, obviously this has to be surface first. So like there is a neighborhood U, which is homeomorphic to open subset of R2. This is what we mean by a surface. Now, for a smooth structure, uh, we need to find a basically this transition maps. Uh, if we have intersecting patches in charts, so these are not the charts, and they are mapped by this one. So let us say this is phi and this is psi. So wherever it is defined, whatever it is, this part to this part, this transition map of phi and psi, this has to be diffeomorphism. Okay. So like if you're taking one patch means one chart and other chart, and if they are intersecting, so basically these maps are diffeomorphism. So we don't have any problem in that one.
I mean, this I understand. Like, mm, isn't it like the definition of manifold itself?
Yeah, that's what.
Yeah, but no, I was asking like, is there some? So you go to a point and
Uh-huh.
you parameterize the neighborhood, right?
Mm-hmm.
So what I was saying, like there can be many parameterization, many
Yeah.
local parameterization.
Mm-hmm.
So first question maybe will be, is there some canonical choice of parameterization. And the second will
Canonical
be,
choice of, yeah,
second doesn't
canonical
make
choice
sense.
of
Yes.
parameterization for what? I mean, like, see the way you define the smooth map on these surfaces. So if you
Mhm.
take a smooth map, you define chart wise. Okay. If two charts are compatible, we don't have any problem to define a smooth map.
Okay, okay.
Okay.
We can
Like
come to
the
maybe later.
okay.
Yeah.
Hi, I'm having
Yes, and
a doubt following the Abhis was asking so I'm canonical in which sense you are asking? I mean, in canonical in which respect you are
No, no,
uh,
no. So, okay, whenever we, I think, seek by canonical, I mean some standalone choice or, uh, yeah. So,
natural choice?
yes, some natural choice. Exactly. Yes. Thank you.
I see. I see. Okay. Thank you.
so whether the doubt is clear or not, I mean,
My doubt is clear. Yeah.
okay. Okay, so let us take a as be an smooth orientable surface in R3, and given an arbitrary point P belonging to S, let so basically 3 be the local parameterization near P. That is, F is a diffeomorphism of an open subset onto a neighborhood of P on S. Okay, so basically the Gauss problem was like Gauss wanted to find a map F which is conformal in the sense that it preserves angle. Okay, we'll see this thing in detail. So basically, by means of this F, we can basically give a line element on the surface S. Okay, by line element, I mean that through which we can calculate the length of the curve. This is the standard. Also, this is also kind of known as first fundamental form of the surface S. So by means of F, the line element ds of S can be expressed in the form ds square is equals to So this is basically the form of this metric. So basically this is ds square is equals to E dx square plus, this is a calculation. I will just write the conclusion of that one. Let's see, this is question 1. So here basically E is summation delta phi square and F is 3 and yes, any doubt? G is basically 3 square. So these are basically these are called the okay. So basically to calculate this one, you can just take the parameterization of the surface around the point P as F, and with this coordinate system, you calculate the line element. So say dx square is equals to dx square plus dy square plus df square. Now this calculate this one. So F is nothing but on F2 and F3. Okay, so all these calculations are this one. Okay. Yeah, observe that. So basically, this kind of expression is basically, it does not depend upon the local parameterization of S. Okay, so for every local parameterization, we will get this kind of expression. Okay. So for our convenience, let us, so convenience, so we will use complex notations. Yeah, but even though Gauss did not. Okay, so basically let us take z is equals to x plus iy, and here we will use dz is basically these differentials, sum of r is basically dx minus I dy. Okay, so basically in this case dx is 1 by 2 dz plus dz bar, and dy is equals to minus 1 by 2 dz minus dz bar. I hope this is fine. And now substitute dx and dy in 1, we get ds square is equals to dz square. So these are just calculations. I will write only the conclusions. Minus 1 by 2 f plus dz bar square 4. We'll have to find e minus g plus 1 by 2 f plus dz bar into 1 by 2 e plus g. Okay, so now this is of the form A, I'm just using some notations. I will clear these things. What are these notations? B dz bar square. We take a common out. Dz plus by a dz bar. Okay. Now write. Wait a minute. Sorry. Mod a square is some lambda. So observe that these are the functions only. So this lambda is lambda of x comma y. Here lambda is nothing but 1 by 4 e plus g plus 2 g plus f square. Okay, and mu is basically b by a, which is e minus g plus 2if upon eg minus f square. So again, this is nothing but on 4 lambda. Okay. Now here's the important thing. So it's important to note that like if you see mu square, this will be nothing but e plus g minus 2 root over e g minus f square upon e plus g root over eg minus f square. So again, this is nothing but less than 1. Okay. So basically modulus of mu is less than 1. Okay. So ultimately what we are getting is ds square is nothing but lambda of x comma y dz plus mu dz bar square, where mod mu is less than 1. Let us call this expression 1. Okay. Okay, now so basically Gauss proved that so basically, yeah, so this f is conformal if and only if E is equals to G and F is equals to 0. Okay. So what does this mean? This means that this condition is equivalent to mu being identically 0. Is it clear? Like, yeah, so if you take E equals to Z, this is going to be 0. Okay. And E equals to Z and F equals to 0. Okay. So this mu is 0. So for F to be conformal, this metric form should look like ds square is equals to lambda mod dz square. Okay. So So basically, this is the idea to define the isothermal coordinates. So, the coordinates with this property is called isothermal. Okay. So what we are basically doing, so we have this surface S, which is a subset of R3, E. Here we have U, and this is our F. Okay. So this is XY. Okay. So Gauss proved that this F is conformal if we have this expression. ds square will be lambda mod dz square. For F conformal. Okay. Now to give a Riemann surface structure on this surface S, see this kind of expression, like reducing to this kind of expression, is not always possible because this mu will not be always identically equal to 0. Okay. So what we want to do is we want to yes.
Yeah, so mu can be 1, right, if E is equal to F square.
Sorry.
I'm saying mu can be 1, right, if E is equal to F square.
Where?
In the definition of mu,
Yeah,
means
this is
I'm
mu.
saying mod mu, no, if you see the mod mu square,
Mm-hmm.
I'm saying if E is equal to F square, then mod mu can be 1. Or is there some condition that EG
No.
cannot be
Okay.
equal to
So
F
that
square?
cannot be 0. Okay, we'll come to that one. Okay.
Sorry, what cannot be
Easy
0?
minus, like this easy
Okay,
minus
I
F
see.
square you're saying. So basically they
Yeah.
are forming a symmetric positive definite matrix.
I see.
So I will come to that one.
Okay, and one more question.
Yeah.
So what is the geometrical meaning of this dx square? We know dx is a dual of tangent space. So
Yeah.
you define some dx square.
Dx
So is
square.
there, yeah, means whenever, maybe before this slide.
This one.
Yeah, and one more before. Yeah, this dx square, or is it dx whole square?
Yeah, dx whole square it is.
Okay, I see.
So these are basically nothing. Yeah, obviously that is if you talk in terms on the tangent planes.
Dual, yeah.
Yeah, so these are the duals because this will dx dy will go to that one tangent space of that one.
Yeah, but then dx dy how will act on the tangent space?
So they are basically make a linearly independent set for the basis. So basically on the tangent space, if you take a curve gamma, we will define the length of this curve gamma by this ds only.
Correct.
Because if you take a curve gamma, its velocity will go to the tangent space.
Yeah. Okay.
Basically,
Yeah,
to
got
get
it.
the
Yeah.
curve. I was telling. Yeah. So the idea is to transform this coordinate to some other coordinate. Let us say, comma v, so that on this coordinate we have this expression looks like in this form. Okay. Now if you are able to coordinate, let us say this is w, if we are able to do so, then this thing will be F composition W inverse. So this will be, by the Gauss result, this will be what? So basically this is going to be conformal. Is it clear, the idea? So basically we want to see, once we have this function f, it is not always the case that this mu is going to be 0. Okay, this one. And here f is a diffeomorphism. So this mu may not be 0. Okay, define a complex structure on this one. Okay, we want to transform the coordinate to a coordinate so that in this coordinate, this metric will be of this form. Okay, suppose this is W. If we take F composition W inverse, by Gauss result, this is going to be conformal. So we'll be having a complex structure on this surface S. Okay, so changing this coordinate W so that the metric is of this form, this is known as the isothermal coordinates. Okay, I will give a precise definition to it. Suppose that in a neighborhood of the origin in the xy plane, there are four real valued continuous function. Just denoted by GIK. Okay, so which satisfies positive and basically G okay. Now we shall say that transformation of
Is it G11, G22 or G11, G12? Or maybe I don't.
where
You said G11, G12 is strictly positive. Is it G22? No, above this one.
this one.
G11, comma G12 is strictly positive. I'm saying
Yeah,
G12
this
or
is extremely
G22.
positive.
Okay, okay.
Like as the
No, I'm thinking
single
of
element.
this is maybe matrix, so maybe G
Yeah, this will
instead
form a
of G.
matrix. So with this
Uh,
condition, can you check that it is positive definite?
yeah, then that should be G22 there. You said
Okay.
G11, comma G12 is strictly positive now.
Wait a minute. So this is symmetric. Oh, sorry.
Yeah, okay. No, before that you write na G11, comma G12 is strictly positive.
This one.
Yeah, so I'm
Oh,
saying
sorry.
G11 and G22 is
G2.
strictly positive.
Yeah, correct. Yeah, sorry.
Yeah.
So this is basically so basically this GIK is element of symmetric. coordinates given by u is equals to u of x comma y, v is equals to with square is nothing but ds square, okay, where lambda is continuous and ds square is basically our g11 dx square plus g12 dx dy dy square, okay. So such transformation, such coordinate transformation u and v, so that it satisfies this one, okay, this basically introduce uh, isothermal coordinates, okay. And
Is it also the case lambda is non-zero or lambda can be any continuous function?
lambda will be positive here.
Okay.
Isothermal coordinates. Isothermal coordinates. Coordinates to this neighborhood, okay, and the function u comma v are called isothermal parameters. Okay. So basically, what we want to do is we want to convert this coordinate into an isothermal coordinate. Okay. So for that, what we need to do, suppose let us we transform this one, W. So here the coordinates will be u comma v. Okay. And let us say this is u dash. Okay. So now transform.
Sorry, do we know W explicitly or have you defined? I mean, I didn't get it. Means is
Which one?
W is some explicit form or is any
So
diffeomorphism of W?
we are mapping this u. So this is in C. Okay.
Yeah.
To a subset in C, we are changing the coordinates. So obviously, like
Okay.
if you meant like this coordinates will be, so like if this z is going to w, so xy is coming into u and w, u and v.
Okay. Okay. So we don't know yet what is explicit form of this
Form of the w.
transformation.
That will
Okay.
come later.
Okay.
That is the main thing here. Even we don't know the existence yet, isn't it?
Yep. Yeah.
Yeah.
So we are doing a priori estimates, kind of.
Yeah. So first we assume, suppose exist,
Yeah.
what we will get. Okay.
Correct. Yeah.
Transform
Do we
the
get some
coordinate.
PD? Okay.
Yeah, we'll get the PD.
I see.
Transform the coordinate by 2. Okay, just let me know whether this thing is clear why we are even uh, transforming the coordinates. Is it clear?
Otherwise, you can't write ds square as a some
Exactly,
positive
yeah.
function times dz square.
Yeah, because once we because once this transformation becomes also thermal, here to here, on this one, like this du square and dv square, okay, this will satisfy this form.
I see.
Yeah, so like Gauss proved that this F map is conformal. This F is conformal if this z coordinate in this one we have this expression. Okay, and those are if and only. So if we
I
have
see.
such yeah.
Sorry. Yeah.
So if we have such expression of the metric here, then this map will be conformal. Okay? So that is our job, to find this isothermal coordinate. Okay, so now transform the coordinate xy to u of x comma y, d of x comma y, where right u plus iv is equals to w. Okay, so note that what would be this du square plus dv square? This is nothing but dw and dw bar. Okay, dw square. Okay, what is dw? Anyone?
Del w by del x dx plus del w by del y dy. Or do you want in d and
Basically,
d
I will
bar
write in
or
the
just?
z and z bar.
Okay, then
This will be
I see.
dz, dz bar. Okay. Now, this dw is basically wz dz plus wz bar upon wz. Sorry. Okay. So, it appears now it is clear. So it
Why is
appears.
wz non-zero, or do we assume
Yeah.
wz
So
is
that's
it?
how, so that's what I'm writing. It
Okay. Oh, I see.
appears that we require wz bar is equals to mu wz, and wz is non-zero with this mu. Okay, so this is a PD. Okay, and this is known as the Beltrami equation. Okay, this is our requirement. Okay, so what we have done is that all these things, this calculation gives us this form. Okay, this form. Okay, now we uh, we want to transform this coordinate, this z coordinate here, this z coordinate to this u comma v coordinate, so that this w should satisfy this one. Okay. Okay. Whether is it clear that if w will satisfies this thing, this Beltrami equation, then that coordinate w coordinate will be isothermal coordinate. Whether is it clear?
Yep.
Mm-hmm. Ravi,
Yeah.
anything?
Yep. I'm saying it will be clear.
Yeah. Why?
Because you can put all the thing there, and then whatever you showed earlier, then it will be of the form dz plus mu dz bar.
Yeah. Exactly. So basically, we can. Uh, basically, this gives us that. So w gives as isothermal parameters. Wait a minute. So I should explain it here. So WZ bar is equal to mu WZ with mod mu is less than 1. Let's call the Beltrami equation. Okay. So if W is a solution of this Beltrami equation, then W gives us isothermal parameters. Okay, isothermal parameters U and V. Basically, one can check that du square plus dv square is nothing but lambda ds square. Okay. Now, is it clear?
Yep.
Yeah. Okay, so now things are done. So now the question is, whatever mu we are getting, like with this process, so this process is giving us mu. Okay, whatever the mu we are getting, can we get W? Whether the question is clear? Means now the problem of finding isothermal parameters to introduce isothermal coordinates is reduced to finding the solution of the Beltrami equation. Is it clear?
Yep.
Let's write it down. So shows that problem of finding isothermal parameters to introduce isothermal coordinates is reduced to finding the solution of the Beltrami equation. So here is a remark. So basically, Gauss proved the existence of a solution of Beltrami equation when mu is real analytic. So you might be wondering that mu is always like whatever the surface I took, mu is going to be smooth, isn't it? At least continuously differentiable or a smooth surface. So like, see, I'm assuming the smoothness, by which I mean this smooth structure is yeah. So here smooth, by a smooth transition law, f and f inverse, I mean that all the partial derivatives of all order exist. Okay. You can have different order of smoothness structure on a surface. If I say C2 smooth structure. By that I mean that transition map is C to smooth. Okay, so in that case, mu is going to be continuously differentiable. Okay,
Okay, sorry. Here f is defined on only on surface. So how can you define the partial derivative on this f, small f, or f inverse, whatever? One of them is defined on surface, right?
this thing.
Yeah, say f inverse. We, you are saying
So
we
F
can take.
inverse. Uh, yeah, wait. So F inverse. Yeah. So here at point P belongs to S, we are
Mhm,
taking F as the local parameterization near P. So this
correct. So
is a diffeomorphism of an open subset onto a neighborhood of P of S. Like this will be there,
uh,
and this neighborhood is always a subset of R3.
oh, I see. I
Yeah.
thought B is a
So
subset of S.
yeah, so like I am taking a smooth surface in R3. So in that case,
Okay.
smooth structure becomes easy. They are abstract smooth surface which cannot be embedded in R3.
I see.
Yeah. So like for convenience, I'm assuming all these things. A smooth surface in R3. Okay.
Uh, okay. Otherwise, we can do covariant derivative and so on. Maybe in say in general Riemannian manifold, can we do
Okay.
all
Yeah.
this
Then
thing in?
exactly. So in that case, we need to define a metric tensor on the surface S. Like
Yeah,
we need to assume that the surface S has a metric tensor. In a sense,
I see.
it has a Riemannian metric.
I see. Okay.
Okay, and in that sense, all this differentiation, all this dx dy will become a one form or one
Covariant
comma one
derivative.
form.
Yeah.
Okay, so in our case, things are okay. But I just want to say that it need not be the case that this mu is always like has a good smoothness thing. Okay, smoothness property. Okay, like if I assume that this surface S has a C1 structure, this mu is only continuous, nothing else. Okay, so basically that is a good, I mean, that is again a hard thing to find out the solution for when mu is continuous, like if you don't have any smoothness assumptions. Okay, so Gauss proved it for uh, this Beltrami equation when mu is real analytic. So people who are familiar with the quasi-conformal mappings, these means Gauss proved that this W exists if whatever mu we are getting here is real analytic. Okay. So if people are familiar with the quasi-conformal mappings, this is nothing but quasi-conformal. This is a solution of a Beltrami equation. Okay. And there is in general theorem for a measurable mu with mod mu is less than 1 by Alfors and Bierling, which is called the measurable Riemann mapping theorem. Okay, which is regarding the existence of this quasi-conformal mappings. That is just about for the further reading. Okay. So basically this uh, isothermal coordinates define a natural complex structure. Can anyone tell me why is this so? Basically, isothermal coordinates are giving us a complex structure on the surfaces. Anyone? So suppose this, okay, I will just explain. So suppose this W is giving us isothermal coordinate. Now this map, composition W inverse, this is going to be conformal. Okay. Now, okay, so this will be a small exercise. So now, if we have, say, U and P, this is,
Abhishek,
yes.
you have 5 more minutes. We will
Okay,
try
okay,
to.
yeah, I will complete in 5 minutes. So this is U and V. This is, let us say, this is WU. Okay, and this is WV. And this is our map phi between this to this. So this phi is going to be conformal isomorphism. This is regarding if, like, if for the same patches, the coordinates which you are getting U and V, if they are intersecting, these isothermal coordinates are basically the transition map phi in between these isothermal coordinates. This is basically going to be conformal isomorphism. This phi is nothing but WV composition WU from WU intersection V to WV of U intersection V. Okay. So ultimately, what we have proved is that every smooth table surface in R3 can be made into a Riemann surface. Okay. So for further reference, I will write a reference. Riemann was on this one, chapter 3, 4, 5, and 6. So this basically will tell us that surface with the Riemannian metric can be made into a okay. So this method will tell us this one. Yes, I'll stop here. Thank you. Hello. So any doubt?
So here PD, this Beltrami operator will exist when mu is some measure, which measure? Means you said
Yeah,
there is some
like
deep
that
result.
is a result by Alphonse and Berling, known as miserable Riemann mapping theorem.
I see.
It says that, so it is in terms of quasi-conformal mappings. Okay. So it says that once you have a measurable mu on a domain in C with mod of mu is less than 1, there exists a quasi-conformal mapping on that domain, such that the complex dilatation of that quasi-conformal mapping is nothing but mu, almost everywhere.
I see.
But
And if I
in
mu
our
just be
case,
smooth.
yeah,
In
so
our
that's
case,
what I'm saying. So in our case, since we have smooth orientable surface in R3, So the kind of mu we are getting, that is continuously differentiable.
Yeah, or maybe smooth. Yeah.
Yeah, smooth. So that W which we are getting, that is also again going to be smooth, because of the, like this result is there. For smooth mu we are getting smooth
I
W.
see.
Yeah. So in the smooth case everything is fine. For
Okay.
general, like in very much general cases, like this is a good reference. Lippmann-Bose lectures on Riemann surfaces.
I see. Okay. Thank you.
Thank you.
Anyone else? Any other doubt? Okay. If not, let us end the meeting here.
Okay, yeah, thank you.